Hello, my dear dreamers, and welcome back to Hayfi Sleep, where we calm the mind and expand the universe one star at a time. Whether you're tuning in to unwind after a long day, to drift off into a peaceful slumber, or simply to get lost in a story bigger than ourselves, I am so incredibly glad you're here. Tonight, we're going on our grandest adventure yet. We're leaving all our everyday worries behind and stepping out our front door, not just onto the porch, but into the cosmos itself. We're going to answer a seemingly simple question that has a truly breathtaking answer. How big, actually, is our home, the Milky Way galaxy? We're going to shrink the universe down to a scale we can understand, and in doing so, I promise you will see the night sky and your place in it in a completely new light. This is a story I'm so excited to share with you. If you're enjoying our journey together, please do consider subscribing to Hayfi Sleep. It truly helps this channel grow and allows me to bring more peaceful explorations to you. And if you're feeling it, give this video a like. It lets me know what kind of stories you love. I'd also love to hear from you in the comments below. Where in the world are you listening from tonight? And what time is it for you? Are you cozying down for the night? Or is this your morning moment of calm? It's always wonderful to feel our little community of stargazers stretching across the globe. So now, find your most comfortable position. Take a gentle, deep breath and let your imagination float free. Let's begin our journey to understand the magnificent scale of our galactic home. You know, sometimes on a really clear, dark night, far away from the glow of the city lights, you look up and you see it. That faint, hazy band of light stretching across the sky like a river of spilt milk. The Milky Way. It's been a constant, silent companion to humanity for all of our existence, a source of stories, myths, and wonder. We point to it, we name our galaxy after it, and we feel a sense of connection to it. But I have to ask you a question, a really simple one, and honestly, the answer is going to blow your mind. How big actually is it? I mean, we hear the words, the Milky Way galaxy. It sounds grand, doesn't it? Immense. But what does that mean? Is it as big as, say, the distance from the Earth to the Moon? Is it bigger than our entire solar system? The words we use can become so familiar that they lose their meaning, like saying a billion years. It just rolls off the tongue. But the reality of it is almost impossible for our brains to truly grasp. So, let's try. Let's take a journey, not on a spaceship, but with our imaginations and really truly try to understand the scale of our cosmic home. And I promise you, by the end of this, you will never look at that hazy band of light in the same way again. First, we need a starting point. Let's start with something we know. You, sitting there, listening to this, or me, standing here talking. We are about, on average, let's say 1.7 meters tall, roughly. That's our scale. Our world, the Earth, is about 12,742 kilometers in diameter. Now that number, 12,742 kilometers, is already too big to really feel. So let's shrink it down. Imagine a beautiful, polished marble about 1 centimeter across, a lovely blue and white swirl. That's Earth. This little marble is our entire world, everything we've ever known, every person, every ocean, every mountain range, all contained on the surface of this 1 centimeter sphere. It's humbling, isn't it? So, let's just pause for a moment on that thought, shall we? This 1 centimeter marble, this entire world. It's a powerful image, but how did we even arrive at it? How do we know with such precision that our home is 12,742 kilometers across? It's not like we can wrap a giant tape measure around the equator, right? Well, the story of how we learned the size of our own planet is a testament to human curiosity and cleverness, and it started a very, very long time ago. Imagine this. Over 2,000 years ago, in ancient Egypt, a man named Eratosthenes. He was the chief librarian at the famous Library of Alexandria, a place teeming with all the knowledge of the ancient world. He heard about a curious phenomenon in a town called Syene, to the south. There, on the summer solstice, at noon, the sun would be directly overhead. So perfectly overhead that it would shine straight down the deepest wells, lighting up the water at the bottom and vertical pillars would cast no shadow at all. Nothing. The sun was just right there. Now Eratosthenes, being a brilliantly inquisitive mind, decided to check if the same thing happened in Alexandria. So, on the very same day, at the very same time, he went out and measured the shadow cast by a tall vertical obelisk, and he found a shadow. It wasn't a long, dramatic shadow, but it was there. A definite, measurable angle. This told him one thing for certain. The Earth's surface was curved. If it were flat, both places would have the same shadow or no shadow at all. But they didn't. Using some elegant geometry, he calculated that the angle of the shadow in Alexandria was about 7.2 degrees. Now, a full circle is 360 degrees, and 7.2 is exactly 1/50th of 360. This meant that the distance between Alexandria and Sienne had to be 1/50th of the Earth's total circumference. It was a breathtaking leap of logic. He then hired a bimatist, a professional distance walker, to pace out the exact distance between the two cities. The measurement came out to about 5,000 stadia. Now, a stadium was an ancient unit of length, and while we're not exactly sure of its modern equivalent, if we use the most commonly accepted conversion, Eratosthenes calculated a circumference for the Earth that was within a stunning 1% of the value we know today, about 40,000 kilometers. And since the diameter is simply the circumference divided by pi, that famous number 3.11415, he had in 200 BC effectively determined the Earth was about 12,600 kilometers across. Isn't that incredible? With little more than a stick, a shadow, and a brilliantly logical mind, a man figured out the size of our entire world. Today, with our orbiting satellites and powerful lasers, we've refined that number. We now know the Earth isn't a perfect sphere. All that spinning one full turn every single day causes it to bulge out slightly at the middle, like a person spinning pizza dough. So, the diameter from pole to pole, the polar diameter, is a bit smaller, about 12,714 kilometers. The diameter across the equator, the equatorial diameter, is a bit larger, about 12,756 kilometers. When we say about 12,742 kilometers, we're taking the mean diameter, the lovely, perfect average of those two numbers. So our 1 centimeter marble is a beautifully simplified version of this slightly squashed, beautifully imperfect spheroid we call home. Now let's come back to you, the listener. I started by saying we are, on average, about 1.7 meters tall. That's roughly 5 feet and 7 inches. Where does that number come from? It's a global average for adult men, a kind of cosmic common denominator for humanity. It's fascinating to think that this average isn't static. It changes from country to country and even across time. For instance, due to better nutrition and healthcare, the average height of people in many parts of the world has been steadily increasing over the past century. In some northern European countries, the average for men is now well over 1.8 meters. But 1.7 meters gives us a wonderful, relatable baseline, a personal ruler against which we can measure everything else. And this is where the real magic of our scaling exercise begins. We have our personal ruler, you, at 1.7 meters, and we have our planet's diameter, 12,642,000 meters. To create our model, we are going to shrink everything down proportionally. We are going to divide the Earth's true size by its own diameter to get it down to that 1 centimeter marble. It's a ratio of 1 to 1.274 billion. Every single thing in our model, every distance, every size, will be scaled down by that same mind-numbing factor. So, if you are 1.7 meters tall in reality in our model world, you would be shrunk down to a microscopic 1.33 billionths of a meter tall. That's far, far smaller than a dust mite, utterly invisible to the naked eye. This immediately gives you a sense of just how vast the Earth is compared to us. Our entire physical being is completely insignificant on the scale of the planet itself. But we are imagining this, so you get to keep your perspective. You are a gentle giant leaning over to look at this beautiful swirling marble that contains all of human civilization. Now let's place this marble in its cosmic context, its neighborhood, which is our solar system. Our sun, as we said, is phenomenally big. Its actual diameter is about 1,392,000 kilometers. To figure out how big it is in our model, we take that enormous number and divide it by our scaling factor of 1.274 billion. Do the math, and it comes out to about 109 centimeters. That's 1.09 meters, a sphere that stands just a little taller than the waist of an average adult. Picture a ball as tall as a kitchen countertop or the seat of a bar stool. That's our sun. Now compare that to our 1 centimeter Earth marble. The sun isn't just a little bigger, it is a colossal dominating presence. In fact, you could fit well over 1 million Earths inside the actual sun. The sheer volume is almost incomprehensible, and the distance between them is even more so. The actual average distance from the Earth to the sun is about 150 million kilometers, a unit we call 1 astronomical unit, or 1 AU. Scaling this down by our factor gives us 150,000 divided by 1,274,000, which is approximately 0.11177 kilometers. Now let's convert that to meters, which is 117.7 meters. That's the length of an American football field, including the end zones, or a full-sized international soccer pitch. So picture this. You are standing next to a beautiful, warm, glowing sphere that's about the height of a person. You hold up a tiny 1 centimeter marble, and then you have to walk the entire length of a soccer field to place that marble in its orbit. All that empty space, just for one single tiny planet. The sun is a person-sized sphere, and our world is a marble over 100 meters away. The emptiness is already starting to feel profound. But wait, we are just getting started. Our solar system is so much more than just the sun and the Earth. Let's take a quick tour of the rest of the planetary family in our scaled-down model. Let's start with the inner rocky planets. Mercury, the innermost planet, is a tiny speck, only about 0.38 centimeters in our model, smaller than a peppercorn. It would orbit very close to our person-sized sun, maybe just 45 meters away. Venus, often called Earth's twin, is a little larger, about 0.95 centimeters, almost a 1 centimeter marble like Earth, but a bit smaller and sweltering. It orbits about 86 meters from the sun. Then there's our marble, Earth, at 117 meters. Just a bit further out, at around 178 meters, is Mars, the red planet. In our model, it's a small p, about 0.53 centimeters across. This is the next stop for human exploration, a world that captivates our imagination, and in our model, it's just a reddish pea about half a soccer field further out from Earth. Now, prepare for the giants. The asteroid belt is a scattered collection of dust and rocks between Mars and the next planet. And then, we meet Jupiter. Jupiter is the king of the planets. Its actual diameter is about 139,822 kilometers. In our model, that translates to a sphere about 11 centimeters across. Picture a large grapefruit, a big, striped, beautiful grapefruit. But where is it? It orbits the sun from a staggering distance. Its actual average distance from the sun is about 5.2 AU. In our model, that's over 600 meters away from our person-sized sun. You'd have to walk the length of 6 soccer fields to get from the sun to Jupiter. A grapefruit, 6 football fields away from a person-sized sphere. It keeps going. Saturn, with its magnificent wide rings that would stretch out even further in our model, is about a 9 centimeter orange, and it's a full kilometer away from the sun. Uranus and Neptune, the icy giants, are even more remote. Uranus, a small billiard ball about 4 centimeters across, is over 2 kilometers away, and Neptune, a similar-sized billiard ball, is an almost unbelievable 3.5 kilometers from our central sun. Just let that sink in. In our model, where the Earth is a marble you can hold between your finger and thumb, you'd need to get in your car and drive a few miles to reach the orbit of Neptune. But here's the truly humbling part. Our solar system doesn't even end with Neptune. Out beyond the last official planet lies the Kuiper Belt, a disc-shaped region of icy bodies, home to dwarf planets like Pluto. It extends out to about 50 AU from the sun. On our scale, that's almost 6 kilometers away, and even that isn't the true edge. Enveloping our entire solar system is the theoretical Oort cloud, a vast spherical shell of icy objects that marks the very furthest reach of the sun's gravitational influence. It's thought to extend out to a mind-boggling 100,000 AU. On our 1 centimeter Earth scale, the outer edge of the Oort cloud would be about 10,000 kilometers away. That's the actual distance from New York City to Sydney, Australia. All of that immensity, all of that breathtaking empty distance from a person-sized sun in the center to a 10,000 kilometer distant shell of ice is just our one single solitary solar system. It's the house, the neighborhood, the entire city block in which our little Earth marble lives. And as we will soon see, this entire vast construct is just one tiny speck in an even grander structure. Now, take a deep breath, because we're about to take a step out that front door. The sun is not alone. It's one star among, well, we need a new number. A really, really big number. The Milky Way galaxy, our home galaxy, is a collection of stars, gas, dust, and dark matter all bound together by gravity. And the number of stars in it is staggering. The best estimates from astronomers suggest there are between 100 billion and 400 billion stars in the Milky Way. Let's take the lower, more conservative estimate just to be safe, 100 billion stars. So let's talk about this new number, 100 billion stars. You might be wondering how on Earth, or rather how outside of Earth, do astronomers even arrive at such a figure? It's not like they can count every single star one by one like taking a cosmic census. The method is much more clever, and it starts with weighing our galaxy. Just like you might estimate the number of apples in a bag by knowing its total weight and the average weight of one apple, astronomers first determine the total mass of the Milky Way. They do this by watching how the galaxy spins. Everything in the Milky Way, including our sun, is orbiting the galactic center, held in place by the immense force of gravity. By measuring the speeds of stars at different distances from the center, they can calculate how much mass must be there to keep them from flying off into the void. This is where things get really strange because the mass they calculate is far, far greater than the mass we can see from all the stars, gas, and dust put together. In fact, only about 10% of the galaxy's mass is the stuff we can see. The rest, the overwhelming majority, is something mysterious and invisible called dark matter. It's the hidden scaffolding of our galaxy, and its gravitational pull is the true engine of its rotation. So, once astronomers subtract the estimated mass of this dark matter, they're left with the mass of all the visible stuff. From there, they can estimate how much of that visible mass is locked up in stars, and by assuming an average mass for a typical star, they arrive at that staggering number, 100 to 400 billion suns. It's an estimate, a best guess based on incredible science, and it reminds us that there is still so much about our own home that we are working to understand. Now, let's come back to that beach. You have your 100 billion grains of sand, each one a star. But our sun, our particular grain, isn't just floating in a random, formless cloud. No, it's part of an immense, organized structure, a city of stars with a specific shape and geography. You described it perfectly, a barred spiral galaxy. Let's paint a more detailed picture of this city. Imagine that central bar not as a solid rod, but as a brilliant, elongated hub of stars, a cosmic downtown that is constantly abuzz with activity. This central bulge is thick with stars, many of them ancient and glowing with a reddish or yellowish light. If you could stand on a planet inside this bulge, your night sky wouldn't be black. It would be a perpetual blazing twilight, with millions of stars brighter than Venus is in our sky, all crammed together. It's a crowded, magnificent metropolis, and flowing out from the ends of this central bar are the great spiral arms. Think of them not as rigid, solid structures, but as cosmic traffic jams, or like waves of compression moving through the galaxy. Imagine a busy highway where a slowdown causes cars to bunch up. The cars themselves are always moving in and out of the jam, but the bunch-up itself persists and moves along the road. In our galaxy, the cars are the stars, gas, and dust. As they orbit the galactic center, they enter these spiral arms, these regions of higher density. Here, the gas and dust are squeezed together, and this compression is the primary trigger for the birth of new, brilliant, hot stars. This is why the spiral arms look so bright and dramatic in pictures of other galaxies. They are the stellar nurseries, the vibrant, glowing districts where the next generation of stars is lighting up. The major arms, with names like Scutum Centaurus and Perseus, are the grandest boulevards, packed with both young and old stars. Between them are the minor arms, like Norma and Sagittarius, which are a bit quieter, filled more with gas and pockets of star-forming activity. And this brings us to our own, very specific address in this colossal city. Our solar system, that one grain of sand we've been following, is not in the bright, bustling downtown bulge. It's not even on one of the major glittering spiral arm boulevards. We are, as you said, out in the suburbs, on a quieter partial arm called the Orion Arm, or Orion Spur. We are nestled between the much larger Sagittarius and Perseus arms. Our exact address is about 25,000 to 28,000 light-years from the galactic center. From our quiet suburban porch in the Orion Spur, we have a pretty good, albeit edge-on view of the rest of the city. When we look up at that hazy, milky band in the night sky, we are looking along the plane of the galactic disk, through the crowded streets of our own spiral arm and beyond, toward the even more densely packed stars of the inner galaxy and the brilliant downtown bulge. The dark patches we see within that Milky River are not empty space. They are vast, dark clouds of cosmic dust, blocking the light from the billions of stars behind them, creating what look like cosmic alleyways and tunnels. So, to summarize our cosmic location, we live on a 1-centimeter marble, orbiting a person-sized sun, which is one of roughly 100 billion other stars, all arranged in a vast spinning pinwheel that is 100,000 light-years across. Our little solar system is situated in a quiet suburban arm, roughly halfway from the vibrant center, slowly orbiting the heart of the galaxy at a breathtaking 828,000 kilometers per hour. And even at that incredible speed, it still takes us a long, long time to complete just one trip around, about 230 million years. The last time our sun was in this particular spot in its galactic orbit, the dinosaurs were just beginning their reign on Earth. It's a perspective that is at once both humbling and exhilarating. We are tiny, we are remote, and we are temporary on this cosmic timescale. And yet we are part of it. We have managed to figure out our place in this immense city of suns. We have mapped the spiral arms from within, weighed the galaxy, and counted its stellar citizens. That tiny, conscious grain of life on that 1-centimeter marble has looked up and understood the architecture of its home, a home of breathtaking scale and beauty. And this brings us to the physical dimensions, the actual mileage of this thing. How wide is the Milky Way? If you could somehow get a cosmic tape measure and stretch it from one edge of the galactic disk to the other, what would it read? The answer is about 100,000 light-years. There's that term, light-year. It's crucial we understand this because it's the only unit that makes any sense at this scale. A light-year is not a measure of time, it's a measure of distance. It's the distance that a beam of light, traveling at the absolute speed limit of the universe, covers in one single year. So, let's linger on this concept of the light year for a moment because it's the foundation of everything that follows. Light moves at a speed that is, for all intents and purposes, the ultimate speed limit of the universe. It's 300,000 kilometers per second. To put a little more perspective on that, if you could ride a beam of light, you could travel from the Earth to the Moon in just over 1 second. Think about that. The Apollo astronauts took about 3 days to make that journey. Light does it in the time it takes you to snap your fingers. Now, stretch that out. Not for a second, not for a minute, not for a day, but for an entire year. A single year has 31,536,000 seconds. So, the distance light covers in 1 year is that staggering speed multiplied by that staggering number of seconds. The math gives us approximately 9.46 trillion kilometers. That's 1 light year. A trillion, just to remind ourselves, is a 1 followed by 12 zeros. So 946 trillion is 9,460,000 kilometers. It's a number so vast that it loses all connection to the world we know. We can't picture a trillion of anything, let alone a trillion kilometers. Now, take a deep breath and hold that immensity in your mind. because the Milky Way galaxy, our island universe, is about 100,000 light-years in diameter. That means it would take a beam of light traveling at the universe's ultimate speed, 100,000 years, to go from one edge of our galaxy to the other. Let's just sit with that for a second. Every single thing we see in the night sky, every star, every nebula, is a part of this structure. The light from those stars has been traveling for years, decades, centuries, even millennia, just to reach our eyes. When we look at the far-off regions of our own galaxy, we are looking back in time, seeing them not as they are now, but as they were thousands of years ago. Now, if we do the multiplication, the diameter of the Milky Way in kilometers becomes a number that is almost comically large, 100,000 multiplied by 9.46 trillion. That's 946,000 kilometers, a 9.46 with 17 zeros after it. This number has no analog in human experience. It's useless for anything other than giving us a sense of profound awe and a slight headache. Our brains simply are not wired to process this. We evolved to understand the distance to a water hole, the height of a tree, the walk to the next village. We have no innate sense for a quintillion of anything. So to have any hope of understanding, we must go back to our scale model. We must shrink the universe down to a size we can walk across. Let's return to our beautiful 1 centimeter marble that is our Earth. On this scale, as we established, our Sun is a person-sized sphere about 117 meters away. Now we need to figure out how big a light year is on this same scale. If our 1 centimeter marble represents 12,742 kilometers, then 1 centimeter in our model represents 1.274 billion centimeters in reality. This is our scaling factor. A light year is 9.46 trillion kilometers, which is 9.46 x 10 to 12 kilometers. To find its model size, we divide that by our scaling factor of 1.274 x 10 to 9 kilometer per model centimeter. The math works out to roughly 7,400 centimeters for 1 light year in our model. Now 7,400 centimeters is 74 meters. So on our model, where Earth is a marble, a single light year is represented by a distance of about 74 meters. That's roughly the length of an Olympic-sized swimming pool, or a little longer than an American football field. Now for the grand finale. The Milky Way is 100,000 light years across. So we multiply our 74-meter light year by 100,000. That gives us 7,400,000 meters, which is 7,400 kilometers. What is 7,400 kilometers across? The contiguous United States from the Pacific coast of California to the Atlantic coast of Maine is almost exactly that distance. It's a near-perfect fit. So let's make this real. Picture a map of the United States. You are standing on a beach in Los Angeles, California. That point on the map represents one edge of the Milky Way galaxy. Now you get in a car and you start driving. You drive through the deserts of Arizona, the plains of Texas, the rolling hills of the Midwest, the cities of the East Coast, and finally, after a journey of thousands of miles, you arrive in New York City. That point on the map represents the opposite edge of the galaxy. The entire, vast continental United States is now the stage for our model of the Milky Way. Now, let's populate this continental scale model. Remember our 100 billion stars? In this model, each and every star, each sun, each potential solar system, is represented by a single fine grain of sand. Our own sun, which in our solar system model was a person-sized sphere, has now been shrunk down to one of those tiny, almost microscopic specks. And these grains of sand are not piled up in a desert. They are scattered, with immense amounts of empty space between them across the entire breadth of the United States. And where is our particular grain of sand, our solar system, located? Well, we know that our sun is not at the center of the galaxy. We're out in the suburbs in a spiral arm known as the Orion Arm or Orion Spur, about 26,000 to 28,000 light years from the galactic center. On our USA map, if the total width is 100,000 light years, then halfway would be 50,000 light years. We're a bit closer in than that. If the galactic center is, say, somewhere in the vicinity of Kansas City, then our position, about 2/3 of the way from the center to the edge, would place our solar system, our single grain of sand, somewhere in the vicinity of Omaha, Nebraska. So, from our vantage point on our tiny speck in Omaha, we are trying to comprehend the structure of an entire continent. This model does more than just help us with the width. It also gives us a feeling for the galaxy's thickness. The Milky Way is a flat disk, but it's not two-dimensional. It has thickness. At the spiral arms where we are, the disk is about 1,000 light-years thick. On our USA model, where the width is 7,400 kilometers, 1,000 light-years scale down to about 74 kilometers. So the thickness of the galactic disk where we live is like the height of a commercial airliner's cruising altitude above the surface of our map. Our entire sprawling continental scale galaxy is, for the most part, only about as thick as a short flight is high. It's an incredibly flat pancake. This is precisely why we see the Milky Way as a band in our night sky. We are inside the pancake, looking through its long, star-filled plane. When we look away from the band, we are looking out through the thin edge of the disk into the much emptier intergalactic space. But there's more. At the very center of the galaxy, there is a bulge. This central bulge is much thicker, about 10,000 light-years across or more. On our scale, that's a region about 740 kilometers thick, a much fatter, more rounded hub at the center of our cosmic pancake. And right at the heart of that bulge, at the center of our entire continent-sized model, sits the supermassive black hole, Sagittarius A star. On our scale, this object, which has a mass of millions of suns, would be smaller than a single atom. Its gravitational influence, however, is what helps shape the entire central bulge and anchors the grand rotation of the galaxy. It's the silent, invisible monarch sitting on the throne at the center of everything. So, when we ask, how wide is the Milky Way? The answer is not just a number. It is an experience. It is the feeling of looking at a map of a whole country and understanding that you live on a speck of dust somewhere in the middle of it, a speck that is orbiting another invisible speck at the center. It is the realization that the hazy river of light you see on a clear night is the combined glow of countless other dust specks, stretching all the way from your horizon in Los Angeles to the opposite horizon in New York. The scale is inhuman, but by building these models, by telling these stories, we can, for a moment, almost grasp it. And in that moment, we achieve something wonderful. We make the universe feel a little bit more like home. Let that sink in for a moment. The entirety of human history, every triumph and tragedy, every work of art, every whispered secret, every life that has ever been lived, has all occurred on the surface of a 1-centimeter marble, which is orbiting a single grain of sand, which is located somewhere near Omaha, in a structure that spans the entire width of the United States of America. The sheer, raw, staggering emptiness of space becomes apparent. The distance from our grain of sand to the next nearest one, which is the Alpha Centauri system, on this scale, is about 4.5 kilometers. That's how far you'd have to walk to find the next grain of sand in this vast continental emptiness. It's no wonder space travel between stars is so fantastically difficult. We are isolated in the most profound sense of the word, but we've only talked about the width. What about the thickness? The galaxy isn't a flat disk like a DVD. It's more like a fried egg with a bulging center and a thinner disk. The central bulge, where the long bar of stars resides, is the yolk of the egg. This region is about 10,000 to 12,000 light-years thick. That's still 1,000 light-years of packed stars. The disk itself, where we live out in the suburbs, is much thinner. It's about 1,000 light-years thick on average. So, on our USA scale, if the width is from coast to coast, the thickness of the disk where we are is only about the height of a 10-story building. We are living in an incredibly flat, pancake-like structure on a continental scale. This is why when we look up at the night sky, we see the Milky Way as a band. We are inside the pancake looking through its long, star-filled plane. When we look away from the band, we are looking out of the thin edge of the disk into the much emptier intergalactic space, and thus we see far fewer stars. Now, let's take a trip, an imaginary journey from one edge of the galaxy to the other. We'll hop aboard a magical ship that can travel at the speed of light. We push the throttle forward and the universe blurs around us. We are moving at 300,000 kilometers per second. Let's see what we'd encounter. Now, traveling at the speed of light isn't like traveling in a car or a plane, where you feel the wind rushing past. At this speed, the universe itself undergoes a strange transformation due to the effects of relativity, but for our journey, let's imagine we can simply observe everything as it is, frozen in a single eternal moment of our passage. The universe blurs not because things are moving past us fast, but because we are moving through space itself, a silent, ghostly vessel on the ultimate express train. We begin our journey at the very outer fringe in the galactic halo. Imagine this as the galaxy's remote, sprawling countryside. It's not a place you'd find on most tourist maps of the Milky Way. It's a vast, and I mean vast spherical region that envelops the entire disk of the galaxy like a faint cosmic fog. If the disk of the galaxy is the vibrant lit-up city, the halo is the dark, mostly empty countryside for thousands of miles in every direction, including above and below. It's not completely empty, but it's incredibly sparse. The stars here are few and far between, and they are special. They are the ancient relics, the grandparents of the galaxy. These are population 2 stars, and they are composed almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. They contain very few of the heavier elements, the carbon, oxygen, iron that make up our world and our bodies, because those elements hadn't been cooked up in stellar furnaces yet when these stars were born. They are living fossils telling the story of the Milky Way's violent, chaotic infancy, a time when the galaxy was first pulling itself together from collapsing clouds of gas and through violent mergers with smaller dwarf galaxies. As we gaze out from our ship into this profound darkness, we might see them, these ancient suns, glowing with a steady, often reddish light. They are old and stable, burning slowly, but the real jewels of the halo are the globular clusters. The text mentioned over 150 of them, and each one is a breathtaking sight. Picture a beehive, but a beehive made not of bees, but of stars. A single globular cluster is a dense, spherical swarm of hundreds of thousands, sometimes even millions, of stars, all gravitationally bound together in a space that might only be a few hundred light-years across. To put that in perspective, if our solar system were placed at the center of a globular cluster, our night sky would be filled with tens of thousands of stars as bright as the planet Venus, creating a perpetual dazzling twilight that would outshine the moon. From our ship, as we pass one at a distance, it doesn't look like a collection of individual points of light. It looks like a fuzzy, glowing ball, a celestial dandelion puff made of ancient starlight. These clusters are orbiting the galactic center on long, looping paths that take them far out into the halo and then back in, like bees dutifully, endlessly circling their hive. And then there's the halo's most mysterious and dominant resident, dark matter. We can't see it. Our ship's sensors can't detect it directly. It doesn't emit, absorb, or reflect any light. It is completely and utterly invisible. So how do we know it's here? We can feel it. Well, not us, but the galaxy feels it. The entire galaxy is spinning, and the stars in the outer disk are orbiting far too quickly to be held in place by the gravity of all the visible matter we can see. All the stars, gas, and dust. It's as if you saw a child on a merry-go-round spinning at an incredible speed. But when you looked, there was no merry-go-round, just the child, magically whirling around in a circle. The only explanation is that there is something else there, something we can't see, providing the extra gravitational pull. That something is the dark matter halo. It makes up the vast majority of the galaxy's mass, perhaps as much as 90% of it. It is the invisible skeleton, the gravitational glue, upon which the visible galaxy is built. As we cruise through the halo, we are sailing through an ocean of this mysterious substance, a silent, unseen ocean whose waves and currents dictate the motion of everything we can see. After what feels like an eternity in the quiet darkness of the halo, we begin our descent into the galactic disk. The change is gradual at first. The number of stars per cubic light-year slowly begins to increase. It's like flying over a dark rural landscape at night and seeing the occasional isolated farmhouse light begin to give way to the dim glow of a distant suburb. We are now entering the thin, flat plane of the galaxy. This is the Milky Way's main stellar city, and we are first arriving in our own neighborhood, the Orion Arm. The character of space changes here, It's no longer the pristine, empty void of the halo. Now we are moving through the interstellar medium, or ISM. Think of it as the galaxy's atmosphere. It's a fantastically thin soup of gas, about 99% hydrogen and helium, and microscopic dust grains. When I say thin, I mean it's a better vacuum than any we can create in our best laboratories on Earth. But spread across light years, this thin soup adds up, and it's the raw material for everything. As we travel, our ship might occasionally pass through a region that feels a bit denser, a bit cooler. These are the molecular clouds. These are the nurseries of the galaxy. They are vast, dark, and cold, often dozens of light years across. They are so dense with gas and dust that they block the light from the stars behind them, appearing as black splotches against the starry background. Inside these cosmic wombs, gravity works its magic, pulling pockets of gas together until they collapse under their own weight, heating up until nuclear fusion ignites in their cores, and a new star is born. As we fly by, we might see the glorious glow of one of these newborn stars, a hot, brilliant blue-white infant. Its intense radiation is now beginning to blow away the cocoon of gas and dust that formed it, like a butterfly emerging from its chrysalis. These regions, called emission nebulae, are some of the most beautiful objects in the galaxy, glowing with vibrant reds and pinks from energized hydrogen gas. The stars themselves here in the Orion Arm are a diverse lot. It's a real melting pot. We see the brilliant, hot, blue-white O and B-type stars. They are the rock stars of the galaxy, incredibly luminous, burning their hydrogen fuel at a prodigious rate. They live fast and die young, lasting only a few million years before going out in a spectacular supernova explosion, seeding the surrounding space with the heavy elements they forged in their cores. Then there are the steady, reliable stars like our own Sun, a G-type yellow dwarf. We are the middle class, the stable workers, burning our fuel steadily for billions of years, providing a steady haven for any planets that might be orbiting us. And finally, the most common stars in the galaxy, the red dwarfs. These are the M-type stars, small, cool, and incredibly frugal. They are so efficient with their fuel that they can shine for trillions of years, far longer than the current age of the universe. Most of the galaxy's stars are these dim, red, long-lived objects. As we continue inward, we cross a boundary of sorts, leaving the familiar streets of the Orion Arm and entering the next spiral arm inward, perhaps the Perseus Arm. The scenery changes noticeably. The spiral arms are not solid structures. You don't cross a fence into them. They are like waves of density, like traffic jams on a cosmic freeway. As stars, gas, and dust orbit the galaxy, they move in and out of these arms. But within the arms, the density is higher. The traffic is bunched up. So, as we enter the Perseus Arm, the number of stars in any given direction increases. The spaces between them on average begin to shrink. Remember, it's still mostly empty space. That average gap of several light years between stars is still the rule, but the average is getting smaller. The glow of the ISM is brighter here, the molecular clouds are larger and more frequent, and the brilliant blue-white newborns are more common. It's a more vibrant, more active part of the galactic city. This part of our journey takes tens of thousands of years. We are witnessing the galaxy in ultra-slow motion, seeing the grand structure unfold at a pace that is literally geological. And then we begin to approach the central region. The very character of the galaxy undergoes a dramatic shift. The thin, orderly disk begins to warp and swell. We are entering the bulge. The galactic bulge is the metropolis at the center of our continental-scale city. It's a vast football-shaped or rugby ball-shaped swarm of stars. The orderly flatness of the disk is gone, replaced by a thick, teeming throng of stars in all directions. Above us, below us, all around us. The density here is exponentially higher. Let's put some numbers on it, simple ones. Out where we live in the galactic suburbs, there is about 0.004 stars in every cubic light year. That means you could fit a cube 1 light year on each side around our sun, and you'd find, on average, a tiny fraction of one other star. It's empty. In the bulge, that number skyrockets. In some parts of the inner bulge, there could be over 100, maybe even 1,000 stars in that same cubic light-year volume. Imagine the night sky from a hypothetical planet orbiting a star deep within the bulge. It would be unlike anything we can comprehend. It wouldn't be a dark sky with pinpricks of light. It would be a blazing, perpetual twilight. Thousands of stars would be brighter than the planet Venus appears in our sky. The entire sky would be lit up with millions of stars visible to the naked eye. There would be no true darkness, ever. The combined light of so many stars would be enough to read by at midnight. It would be a sight both terrifyingly beautiful and utterly alien. The constellations would be meaningless. The sky would just be a solid, shimmering sheet of starlight. And at the very heart of this brilliant, dense, chaotic metropolis lies the anchor, the reason for all this crowding, the supermassive black hole, Sagittarius A star. We cannot see it. No light can escape it, but we can see its terrifying influence. We can observe stars orbiting frantically around nothing. They whip around this invisible point at speeds of thousands of kilometers per second, their orbits telling us the mass of the object they are circling. That mass is about 4.1 million times the mass of our Sun. Now, it's crucial to correct a common misconception. Sagittarius A star is not a cosmic vacuum cleaner, actively sucking everything in. From our distance, it's a gravitational anchor. Its influence is vast, but its physical size is tiny. Its event horizon, the point of no return, is only about 24 million kilometers across. That's smaller than the orbit of Mercury around our Sun. On our USA scale model, it would be smaller than a single atom at the very center of the continent. It's a pinprick of ultimate density, a silent, dark king sitting on the throne, its immense gravity governing the frantic dance of the stars around it, helping to shape the entire bulge that surrounds it. We fly past this monstrous, invisible presence and continue on our way, out through the bustling, star-choked bulge, back into the thinning disk. We pass through the spiral arms on the far side of the galaxy, a mirror image of our own side, watching the stellar density gradually decrease, the brilliant blue star-forming regions becoming less frequent, until we once again break through into the sparse, dark, and ancient countryside of the outer halo, finally emerging from the opposite edge of the galactic disk. We have done it. We have crossed the Milky Way. And how long did this magical light-speed journey take? 100,000 years. 100,000 years. Let's make that number land. Modern humans, Homo sapiens, have only been around for about 200,000 to 300,000 years. Our light-speed journey across the galaxy took half that time. All of recorded human history, the building of the pyramids, the rise and fall of Rome, the scientific revolution, the creation of the internet, all of that fits into the last 5,000 or 6,000 years. Our journey took 20 times longer than all of that. We were traveling at the ultimate speed limit of the cosmos, and it still took us an epoch. That isn't just a number. That is the final, humbling, and utterly inescapable truth of the sheer, mind-boggling scale of our galactic home. It is a vastness that transcends human history, a stage so large that our entire story is but a fleeting whisper somewhere in its quiet suburbs. But the story of the Milky Way's size isn't just about its stars and its empty spaces. It's also a story in time. We've been talking about the Milky Way as it is now, a magnificent spinning pinwheel of stars. But to truly know something, you have to know its story. Where did it come from? What shaped it? And where is it going? The size of our galaxy isn't just a snapshot. It's a single frame in an epic movie that has been playing for almost the entire age of the universe. So let's rewind the cosmic clock all the way back to the beginning. The universe itself is about 13.8 billion years old. Our galaxy, the Milky Way, is a cosmic elder. It began to form not long after the Big Bang itself, around 13.6 billion years ago. Just let that number sit for a moment. 13,600,000 years. How can we even comprehend such a depth of time? If you condense the entire history of the universe into a single calendar year, with the Big Bang at the stroke of midnight on January 1st, our Milky Way galaxy would have begun forming just a few days later, in early January. The Earth, by comparison, wouldn't form until mid-September. The entire span of human history would be the last few seconds before midnight on December 31st. Our galaxy is ancient beyond our everyday comprehension. But it didn't spring into existence as this beautiful organized spiral we see today. That came much, much later. The early universe was a very different place. It was a dark, swirling sea of primordial gas, mostly hydrogen and helium, and that mysterious, invisible dark matter. There were no stars, no galaxies, just a faint, fading afterglow from the Big Bang and these vast, slowly cooling clouds. Gravity is the great sculptor of the cosmos, and it went to work on these clouds. Tiny, random ripples in the density of this primeval soup began to amplify. Patches that were ever so slightly denser began to pull more matter towards them. These were the seeds, the protogalactic clouds, that would one day become galaxies. So, picture the infant Milky Way not as one single thing, but as a chaotic, swirling mess of dozens, perhaps even hundreds, of these smaller gas clouds and clumps of dark matter, all slowly, inevitably, falling together and merging. It was a violent and chaotic process, a cosmic demolition derby that lasted for billions of years. There was no gentle coming together. It was a series of colossal collisions. With each merger, the growing baby galaxy would get a jolt. Its gas would be stirred up, triggering furious waves of new star formation. The sky in those early epochs would have been a terrifyingly spectacular sight, filled with the brilliant, short-lived flashes of massive first-generation stars going supernova, their explosions seeding the surrounding gas with the first heavy elements, the carbon, oxygen, and iron that would one day be essential for planets and life. And this process of growth through cannibalism never really stopped. Our Milky Way is not a peaceful, isolated island. It exists in a gravitational neighborhood, and it is the biggest, most massive kid on the block. It has a powerful gravitational pull, and it uses it to consume its smaller neighbors. It continues to do so even today, right now as we speak. We have the evidence. Astronomers, using powerful telescopes, can see the ghostly trails of stars stretching across our galactic halo. These are tidal streams, the cosmic scars of dwarf galaxies that ventured too close to our galaxy. The gravity of the Milky Way is like a powerful tidal force. It has stretched these unfortunate galaxies out, pulling them apart like cosmic taffy until their stars are no longer a distinct cluster but a long, shimmering river of stars, wrapping around our galaxy in vast, elegant arcs. The most famous of these is the Gaia Sausage, or the Sausage Galaxy, the remains of a dwarf galaxy that collided with the Milky Way about 8 to 10 billion years ago and was utterly shredded, its stars now forming a significant part of our galactic halo. It's a stark reminder that the Milky Way is a dynamic, evolving beast, not a static picture in a textbook. It's a predator, still growing and changing. And this brings us to the future, to the next, and perhaps final great chapter in our galaxy's life story. It's not done growing. In about 4 to 5 billion years, the Milky Way is destined for the collision of a lifetime. Our nearest large galactic neighbor, the beautiful Andromeda galaxy, is on a collision course with us. Now, when we say collision course, it sounds terrifying, like two cars smashing into each other on a highway. But we must remember the most important lesson we've learned about our galaxy. Its overwhelming, dominant feature is not the stars, but the empty space between them. Andromeda is hurtling towards us at a tremendous speed, about 110 kilometers per second. That's fast enough to travel from the Earth to the Moon in under an hour. But the distance between us is so immense, about 2.5 million light-years, that this cosmic rendezvous is still billions of years away. So what will happen when we meet? It will not be a catastrophic crash of stars. It will be a slow, majestic, gravitational dance. The spaces between stars are so phenomenally vast that when the two galaxies merge, it is incredibly, almost unthinkably unlikely that any two stars will actually physically collide. It would be like taking two handfuls of fine sand and tossing them into the wind so that they pass through each other. The chances of two individual grains of sand hitting each other are virtually zero. Instead, picture two vast swarms of bees, each containing hundreds of billions of bees, gently passing through one another. Each individual bee, each star, will follow its own path, largely unaware of the others, guided only by the combined gravitational field of the entire swarm. They won't crash. They will swing past one another in long, graceful arcs, but their overall shapes will be utterly distorted. The beautiful, delicate spiral arms of both the Milky Way and Andromeda will be stretched and torn apart by tidal forces. The two galaxies will become a tangled, messier, and much larger blob of stars. They will swing past each other, then fall back together, and then swing past again, in a series of ever-tightening loops over the course of 1 billion years. It will be a slow-motion merger, a cosmic ballet choreographed by gravity. Eventually, after this long, chaotic dance, the two galaxies will lose their separate identities and settle down, merging into a new, larger type of galaxy. The neat, flat spiral disks will be gone, replaced by a more featureless, football-shaped swarm of stars called an elliptical galaxy. Astronomers have already given this future galaxy a name, milkomeda. It's a fitting name for the combined legacy of our two great star cities. What will happen to us, to our solar system, during all this? Our sun will still be shining then, though it will be brighter and older. Our solar system will likely be flung out into a much different, much larger orbit within this new milkomeda galaxy. We probably won't be anywhere near the new galactic center. We'll be thrown out into the distant suburbs, but we will almost certainly survive the encounter physically. The real change will be in the sky. For any beings living on Earth at that far future time, perhaps our descendants, perhaps something else entirely, the night sky will be utterly transformed. It will be a dazzling, constantly changing display. As the merger progresses, the Andromeda galaxy, which today is a faint, fuzzy smudge in our sky, will grow larger and larger, eventually filling the entire heavens. The familiar band of our Milky Way will be joined by a second brilliant river of light, and then the two will churn together into a spectacular, chaotic canvas of countless stars. It will be the greatest light show in the history of our planet, a billion-year-long fireworks display marking the end of our galaxy as we know it and the birth of something new and grand. It's a story that stretches from the very dawn of time to a future so distant it challenges imagination, and it's the story of the home we are just beginning to understand. So when we ask, how big actually is our Milky Way galaxy? We have to think in multiple dimensions. It is big in population, 1 to 400 billion stars. It is big in space, 100,000 light-years across, a continent of emptiness with grains of sand for stars. It is big in time, a 13.6 billion-year history of formation, growth, and future collision. And it is big in mass, containing not just the visible stars and gas, but dominated by the mysterious, invisible hand of dark matter, whose gravitational pull is the true architect of the galaxy's grand design. We are a part of this. The calcium in your bones, the iron in your blood, the oxygen you breathe, these elements were forged in the hearts of long-dead stars that lived and died in this galaxy before our sun was even born. We are not just living on a planet. We are living in a galaxy. We are the Milky Way, become conscious of itself. We are a tiny, fleeting part of this immense, rotating, evolving cosmic structure. So the next time you find yourself under a clear, dark sky, look up. Find that faint, milky river of light, and remember what you are truly looking at. You are not looking at a distant external thing. You are looking at your home. You are looking edge-on into the disk of a continent-sized city of stars from your vantage point in the quiet suburbs. You are seeing the combined light of billions of distant suns, the central bulge glowing like a distant city center, the dark lanes of cosmic dust clouds blocking the light from beyond. You are seeing the scale of your own existence. It is a humbling, awe-inspiring, and profoundly beautiful sight. And now you know just how big it actually is. And so, there you have it. Our little marble, orbiting its grain of sand sun in a quiet suburb of a continent-sized city of stars. A city that is itself growing, changing, and dancing with its neighbors in the infinite black. It's a perspective that is at once both humbling and incredibly uplifting. We are so small, and yet we are a part of this. We get to be the part that can look up and understand and feel awe. I hope this journey across the cosmos has brought a little wonder and peace to your evening. Wherever you are, Whatever time it is, I hope you carry this feeling of cosmic connection with you as you drift off. If this peaceful exploration helped you unwind or see the universe in a new way, please consider supporting our community here on Happy Sleep. Subscribing to the channel helps you never miss our next journey into relaxation and wonder. And if you felt inspired, leaving a like is a wonderful way to let me know. Most of all, I'd love to hear from you. As you float here in our little corner of the Milky Way, tell me in the comments, where in the world are you listening from tonight? What's one thought or feeling you're taking with you from our journey? From all of us here at Happy Sleep, thank you for sharing this time and space. Sleep well, dream deeply, and may your dreams be as vast and peaceful as the galaxy itself. Good night.